Hello all, welcome back. In the last lesson we talked about solubility rules, and we tried to go through and decide what sorts of ionic compounds were soluble. If you can remember, the easiest way to remember which ionic compounds are soluble, you can just use the acronym CASH and GIA. I cleaned up this slide a little bit because it kept causing my computer to crash. It looked like it was like entering another dimension twice. So these are the ions that are always soluble: chlorates, acetates, sulfates, halides, nitrates, group 1 metals, and ammonium. Now there were a couple exceptions to this that confused a lot of people, or they tend to be confusing, is the sulfates and the halogens or the halides. So there are combinations of metals with these two types of ions that do not dissolve. So almost all sulfates are soluble except calcium sulfate is not, strontium sulfate is not, and so forth. Almost all chlorides and bromides are soluble, but lead 2 chloride is not, lead 2 iodide is not, mercury iodide is not, and so forth. So these are just a few exceptions. There are some other exceptions going the other way. There was one in the worksheet where there are a few hydroxides that you would assume that they're not soluble, but they are. Those are a little bit harder to list with an acronym, and they hardly ever come up. Frankly, if you actually work with these compounds, they're really not that soluble. A solution of barium hydroxide, it just barely dissolves, but for some reason it always shows up in textbooks as soluble. So I don't really think that those are that worth mentioning, and they're in your chart anyways if you're really interested in them. So what I want to talk about today is reactions with ionic compounds that are soluble or insoluble. So this is the whole purpose of this chapter, and this is something that if we're able to get back to school in May, something that we're going to be working with are reactions between soluble and insoluble compounds. So what you end up getting with this is called a net ionic equation, or a precipitation reaction, as they're sometimes called. So we went through and we decided what's soluble and what's not soluble. A net ionic equation describes, I'm going to put this in parentheses here, a net ionic equation describes a precipitation reaction. So a reaction where you have two liquids or two dissolved compounds that mix together and they form a compound that's not soluble. So we described this as two liquids creating a solid when we did this in the reactions chapter. So I have here an example of dissociation reactions that we were writing. So these are two different soluble ionic compounds. I've got sodium chloride and lead 2 nitrate. Remember, it's lead 2 because there's twice, it's got a positive 2 charge, so I need 2 nitrates to go along with it. So sodium chloride dissolves, so if I dissolved it in a liquid, or if I dissolved it in water, it would separate into sodium ions and chloride ions. And if I took lead 2 nitrate and I put it in liquid water, it would separate into lead 2 ions and nitrate ions. So as a result, I would have to do this in separate containers, because if I mix them together, what would end up happening is, look, I have this is lead chloride or lead nitrate dropping into sodium chloride. What ends up happening is immediately a solid starts to form, because in this solution of 4 different ions, you have a combination that is not possible. If you had all 4 of these ions mixed together, one of those pairs, one of those possible combinations of ions would not dissolve. So either the inside pair of ions, so if we write this out as all the different ions together, so what I'm doing here is I'm just saying this was sodium chloride just separated into 2 parts, and this was lead nitrate separated into 2 parts. So when you dissolve in water, they separate, but when I mix all 4 of them together, what ends up happening is lead chloride, according to our solubility rules, Lead chloride's an exception. Lead halides do not dissolve. Lead chloride should not be soluble. So if I have all four of those ions in the same place at the same time, what ends up happening is lead chloride precipitates out. Remember, from double replacement reactions, the way that we predicted the products was always inside outside. So you can say that, I'll do this with the way that they're going to swap partners is chloride could go with lead and sodium could go with nitrate. So this is basically the different possible combinations that you could have. However, sodium nitrate is always soluble. Remember, so this is group 1 and this is a nitrate, so those things are always soluble. So as a result, only one of the two possible combinations of ions is not going to dissolve. So it precipitates out as a solid. Now this is where I really hate that both of those words start with S. This S here represents that a solid precipitate is forming from the reaction. That's the only reason we write it there. It doesn't mean soluble. If it was soluble, it would separate into different ions. And by the way, these would be aqueous if I labeled them here. Because the sodium chloride is still the sodium nitrate at the end of the reaction, the other two ions that did not form as solid precipitate, these are still soluble, these are still dissolved. So they're not really doing anything as part of the reaction. All they were doing was they were mixed in with the other two ions. So what we do with these is we cross them off. It's just like in algebra. If you have something that you can subtract in the exact same way from both sides, you can just cross it off. And so sodium appears in the same way on both sides, and nitrate appears in the same way on both sides. And ignore this because we're going to balance at the end here. But chloride and lead, you can't cross them off because on one side of the reaction, they're ions. They're dissolved in water as ions. And on the other side of the reaction, they're stuck together as part of a solid. You can look at that kind of on a virtual level here. This is with a different compound, but you still see the example that they're all kind of mixed in together. But after the reaction, there is a solid that forms where all of these ions link together in a lattice. But then there are still some ions that are still dissolved. And these were dissolved over at the end of the reaction, and they were dissolved in the same way at the beginning of the reaction. So they're not really part of the reaction, they're just watching it. So we refer to them as spectators, spectator ions. Those are things that don't really react, but you need them to mix together your solutions at the beginning. Okay? So we can practice drawing some of these out. If I just were to give you two different combinations of ionic compounds, I would expect you to be able to tell me what the net equation is. So it's net in the sense that you are crossing off things that you don't need, like net profit, your net gain. Those are the net gain, or your net profit is your what you earn minus your losses. So the net ionic equation is the entire reaction minus the things that we don't need. So I wanted to work out an example of what it would look like if I wrote a net ionic equation between two different ionic compounds, tin 2 chloride and silver acetate. So what we're doing is we're dissolving them both in separate containers and then sort of mixing them together. So what we should probably do is write out what these chemicals are first. So tin 2 chloride is SnCl2, and I'm reacting that with silver acetate, which is Ag, and then acetate is C2H3O2. Okay, so these are the things that I'm reacting together. Okay, so I'm going to end up with a precipitate, something that does not dissolve. Okay, so before you do anything else with what the products are here, what I like to do is think about what these different ions are. So the first thing that you should think about is, well, if I'm dissolving this, I'm separating it out into ions. So I'm going to have tin ions and chloride ions and silver ions and acetate ions. And I separate out so I can list all four of what the ions are right here before I even get to the other side of the arrow. So tin 2 should be SN2 plus. And then a chloride ion. Now it looks like you should write Cl2, but that's not right. Chloride, you have to write it exactly how it appears on the periodic table. That's Cl with a minus charge. So that's just going to be Cl minus. Okay, I'm going to put some pluses in between these. Okay, so I've got those two ions, and I'm mixing it together with two other ions, silver, which is just Ag plus, and acetate, which is C2H3O2 minus 1, or just a minus. Okay, so those are the things that I'm reacting together. Okay, so then I should decide what are going to be the products here. Remember, we said an easy way to figure this out is inside outside. So I know that the other combination of ions that would give me a positive and negative in each one would be if I combine silver with chloride and if I combine tin with acetate. So the inside and outside pairs. So my products here are going to be tin acetate and silver chloride. Okay, so that's one way of kind of going through and doing this is tin acetate and silver chloride. I wish I would have given myself a little bit more room here. But, okay, so one of those is not going to be soluble. One of them has to be able to precipitate out. So is it going to be tin 2 acetate or is it going to be silver chloride? Well, you can look at your solubility rules and say, okay, so chlorides fall under this category. Chlorides are soluble. Oh, it came out of focus. Chlorides are soluble except when with silver, lead, copper, and mercury. So silver chloride is the one that's not soluble. And let's double check acetate. Okay. Nitrates and acetates and chlorides are always soluble, no exceptions. Okay, so it can't be tin acetate. The one that's going to be the solid is going to be the silver chloride because it's not soluble, it precipitates out. So I'm going to put a little S after it here. I'm sorry, my webcam can't focus. It's about 10 years old here. So what that means is I probably should be writing tin acetate as ions. And what you can do is figure this step out before you write it out. So you can figure it out before you even write it down. But what I'm going to do is rewrite this as, give myself a little bit more space. I'm going to keep the left side the same. And instead of writing tin acetate as this is still just going to be ions. Okay, so I'm going to make this SN2 plus C2H3O2 minus, and then I'm going to put my silver chloride solid. So it's important that you put that little solid in parentheses. And then the last couple steps are, to figure this part out, you can cross off the spectators, the things that appear on both sides in the same way. So the ones that stayed dissolved the whole time here were tin and acetate. You can always, they're the ones that did not precipitate out like the silver chloride did. So acetate ends up on both sides, and tin ends up on both sides. So I'm going to cross those out. And so my net ionic equation, the final answer should be Cl minus plus Ag plus goes to AgCl, solid. Okay, the one that's over here should never be soluble. If you have a soluble thing on the end of your equation, you didn't do it right. Okay, it has to be something that is not soluble. It has to be a precipitate solid. Okay, and notice this is balanced. So this would be the step where I would put coefficients here if I needed to, but this one just balances to 1, 1, 1. Okay, you can always do that at the last step.